This is Mr. B. Giriraju, Professor of EC Department, AS Engineering College, Hyderabad. So in the last video, I have given explanation for the signal analyzer. So already I have explained explanation for wave analyzer. So with the help of wave analyzer, so you can measure selected frequencies in the form of harmonics, so like that. So generally here, so you can divide wave analyzer in two types. So first one is the frequency selective wave analyzer, and the second one is heterodyne wave analyzer. So your frequency selective wave analyzer, so the frequency is 20 Hz to 20 kHz, and heterodyne receiver wave analyzer selects frequency from 20 kHz to 18 MHz. So actually that having a basic circuit diagram, that basic circuit diagram consists of first primary section in the form of LC network, and next section in the form of rectifier. So your rectifier part will act as a basic meter. So with the help of basic meter, so you can measure test wave. With the help of tuning circuit, you can vary fundamental frequency. That means with the help of LC circuit, so we can tune the frequency. Because of here, LC circuit will act as a tuning circuit. So now with the help of this circuit diagram, so you can study so frequency selective voltmeter. With the help of the voltmeter, you can measure from 20 Hz to 20 kHz frequencies. Actually, this having some circuit basic block diagram. So this is a combination of the some attenuators and so local oscillators. So like with the help of attenuator, you can vary input of the signal, and is also having some Q active filter. So that that active filter will act as a low pass filter. So your output of the active filter, you have to pass to the some driven amplifier. So with the help of that amplifier, you can vary the output of the Q active filter. Finally, you can see output of the frequency selective wave analyzer in the form of some value, so like as 20 Hz and 20 kHz in the meter. So this is the frequency selective wave analyzer. So second one is heterodyne. So is also having first block as attenuator. Now we have to combine this signal with some local actor with the help of mixer. And again in second section also, you have to combine with crystal pixel oscillator. So now you have to combine the signal with the help of mixer. So finally, with the help of some driven amplifier, so finally you can measure and you can combine signals of the input and some local oscillator and crystal oscillator. So actually here heterodyne means mixing. That means now here also we are doing like this. This is a function of the heterodyne so wave analyzer. So with the help of this meter, you can measure frequency ranges from 20 kilohertz to 18 megahertz. So these two are belongings to wave analyzers. So next one, distortion analyzer. So you can call it as a harmonic distortion analyzer. So with the help of harmonic distortion analyzer, so you can measure values of the harmonics in the waveform. Actually, your waveform is some combination of the harmonics. So due to some reasons, so you will get some distortion. That means you can observe some variation in the harmonics. So now with the help of distortion analyzer, harmonic distortion analyzer, you can measure such type of variations. So we can call that distortion as total harmonic distortion. So next one, to measure such type of distortions, so we have three methods. First one is the resistance method, second one Wien-Bridge method, last one the T-bridge network method. So here also you have to adjust fundamental frequency with the help of tune circuits. So with the help of bridges also you can do like that. So finally, with the help of tank circuit, you can vary fundamental frequency also. That means here we can do like that. So finally, we have to test wave input. So with the help of some detector. So these are three belongings to harmonic distortion analyzer. So next one, power analyzer. So actually in industries, so power maintenance is also one of the important tasks. So now you have to, every time you have to monitoring the power supply, so in the industries. So that's the reason, so we have to proceed some maintenance process. So with the help of power analyzer, so you can measure such type of variations in the power supply. Actually this is having some sensing elements, that elements connected to some mux multiplexer. So your output of the mux give to analog to digital converter. That means now we are combining all variations in the systems in the multiplexer. Finally, we will take that signal in the form of single output. That output we will convert with the help of analog to digital converter in the form of digital signal. So here we can observe one microcontroller also. That microcontroller will operate according to our programming. So actually whatever we want to, that value we can monitor from the microcontroller. Finally, you can see problems on the display. Display may be the CRO or X-ray recorder, like that. Whatever the display system, finally we can observe our problems in the industries on display. So this is the function of the power analyzer. So next one, I am going to explain spectrum analyzer. Already in the last video I have explained some basic explanation for the spectrum analysis. So once again I will start from beginning of the spectrum analyzer. That means now once again I will explain spectrum analyzer from the beginning stage. Okay, here spectrum analyzer and oscilloscope to display the signals with time as the XY axis. So generally, yes, CRO, with the help of CRO you can measure amplitude, frequency, time in time domain. So it is also useful to display signals in the frequency domain. The instrument provides this frequency domain is called the spectrum analyzer. So generally here we will see output of the generators. So with the help of CRO, that means you have to measure quantities with the help of CRO in the form of waveform. So that may be either voltage, current, or frequency, time, like that. So now with the help of oscilloscope to display signals with time as the x-axis, it is in the time domain. It is also useful to display signals in the frequency domain. Now in that case, you have to take help of the spectrum analyzer because of the instrument provide this frequency domain. U is called the spectrum analyzer. Spectrum analyzer provide a calibrated graphical display on its CRT with frequency on the horizontal axis and amplitude on the verification. So finally here we can see our required output in the form of amplitudes. So actually this instrument provide a display of the frequency spectrum over a given frequency band. Spectrum analyzer use either a parallel filter bank or a swept frequency technique. So in a parallel filter bank analyzer, the frequency range is covered by a series of filters whose central frequencies and bandwidth are so selected that they overlap each other. So as shown in below figure. So actually this is the parallel filter bank analyzer. This having filters in the form of parallel combination from 1 to n values. So here you have to provide some input signal V of t. So every filter will give outputs in the form of parallel. So simultaneous output CRT display, so you can observe like this. So here in a parallel filter bank analyzer, the frequency range is covered by a series filters whose central frequencies and bandwidth are so selected that they overlap each other. So as shown in this figure. Typically, an audio analyzer will have 32 of these filters, each covered 1/3 of an octave. So actually this is the overlapping filter bank. So actually here we are taking filters from 1 to n values. So like this. So every value overlapping into each other. So for a wideband narrow resolution analysis, particularly at RF microwave signals, the swept techniques is preferred. So in block diagram. So you can observe, so one mixer and voltage tuned amplifier and sawtooth generator. So detector and video amplifier and IF amplifier. So mixer and one display. So this is the spectrum analyzer. So in this block, the sawtooth generator provides the sawtooth voltage, which drives the horizontal axis element of the scope. So here, so this sawtooth voltage is the frequency controlled element of the voltage tuned oscillator. So this is the voltage tuned oscillator. So this is the sawtooth generator. Sawtooth generator will generate sawtooth waveform. So now this frequency element of the voltage tuned oscillator. As the voltage tuned oscillator sweeps from F minimum to F maximum of its frequency band at a rate. So input signal of spectrum and laser recurring and output of the voltage. Recurring output of the tuned voltage. So beat together to produce a different frequency. That means IF, intermediate frequency. So here the IF corresponds to the component is amplified and detect if necessary and then apply to vertical plates of the CRO. So these are vertical plates of the CRO. Here CR means we are taking spectrum analyzer. So now here we have to provide one signal from sawtooth generator, other from video detector and video amplifier. This will come from IF. So here the spectrum produced if the input wave is single tuned, AM is given as test wave seen or a ordinary CRO. So you can observe our signals are like this. So actually we have to see output in the spectrum analyzer. Now we can observe our output. So like this, actually the spectrum produces the input wave is a single tuned AM is given as a test wave. So actually this is the ordinary, in ordinary CRO you can observe like this. So now we are taking waveform between amplitude and time, so you can observe like this. Actually this is having two waves, so one having frequency F and other having 2F, you can observe like this. So actually here now on spectrum analyzer of the screen you can observe our output waveforms are like this. So here we are taking output between amplitude and frequency. So F and 2F are the frequencies. This having amplitude A1 and other one having A2. So now on screen of spectrum analyzer, you can observe our waveform. Amplitudes are like this. So this is the output of the spectrum analyzer. So actually a spectrum analyzer also having two types. So one is the basic spectrum analyzer using swept, swept receiver design, and other one is the RF spectrum analyzer. So now I am going to explain first one, basic spectrum analyzer using spectrum receiver. So here basic spectrum analyzer using spectrum receiver design, one of the principal application of the spectrum analyzer, study of RF spectrum produced in microwave instrument. In microwave instrument, the horizontal axis can display as a wide range 2, 2 to 3 gigahertz for a broad survey, and narrow as 30 kilohertz for a highly magnified view of any small portion of the spectrum. The frequency covered by this instrument from 1 megahertz to 40 gigahertz. So the basic block diagram of spectrum analyzer covering range 50 kilohertz to 1 gigahertz, which is represented as super heterodyne type. So this is the our block diagram of spectrum analyzer using RF receiver. So this is called the heterodyne type of RF spectrum analyzer. So your input signal 0 to 1 gigahertz is fed to mixer, which is driven by local oscillator. This local oscillator is linearly tunable over to range 2 to 3 gigahertz. So your mixer will provide, two signal as is output proportional in amplitude to the input signal, but of frequencies which are sum and difference of the input signal and a local oscillator. If amplifier is tuned to the input signal, but of frequencies which are sum and difference of the input signal and local oscillator. So if amplifier is tuned narrow band, frequency around 2 to gigahertz, because of low oscillator is tuned the range 2 to 3 gigahertz. Detector detects the output of the IF amplifier. So get received and produced a vertical deflection of the spectrum analyzer. Actually, spectrum analyzer also having some CRT. So now your vertical amplifier will provide signals to vertical deflection plate of the CRT. It is observed that as the sawtooth signals sweeps, the local oscillator also sweeps similarly from 2 to 3 gigahertz. The timing of the spectrum analyzer sweeps Thus, the timing of the spectrum analyzer is a swept receiver, so which is sleeps linearly from 0 to 1 GHz. So the sawtooth wave signal also applied to horizontal place of the CRT. So this is a sawtooth generator. This will generate a sawtooth wave to horizontal place of the CRT. So this is the function of the RF spectrum analyzer. So applications. So actually here spectrum analyzers using for the purpose of monitoring enemies actions with the help of radars. So actually a spectrum analyzer widely used in radars, oceanography, biomedical fields. So these are the applications of the spectrum analyzer. So now I am going to explain logic analyzer. So these are the specifications of the logic analyzer. So actually this having number of channels as 68. So maximum state clock speed 200 MHz, maximum timing clock speed 400 MHz. Memory depth for logic state analyzer 256 states. Memory depth for logic timing analyzer 512K samples. Number of op states clock qualifiers 4. So trigger sequence levels 16. Input plus or minus 40 V peak maximum. Voltage swing 50 milli V peak to peak minimum. So range of voltage threshold minus 6 volts to plus 6 volts in 10 millivolts increments. So these are the specifications of the logic handler. So actually here we can observe two types of logic handlers: logic state analyzer and the logic timing analyzer. So now I will explain one by one. So actually this is the basic block diagram for the logic analyzer. So this is the basic block diagram for the logic analyzer. So in this figure shows the block diagram of logic analyzer. Basically, logic analyzers are classified into two types. One is the logic state analyzer, other one is the logic timing analyzer. So in these classifications are based on the operating modes of the logic analyzer. So now first I will explain logic state. First one, logic state analyzer. Logic state analyzer. So here the probe buffer acts as a entry point through which the logic signals are entered into the logic analyzer. So observe here, this is the probe buffer. So you are providing data and clock, external clocks are like this, you can observe here. So now this probe acts as a entry point through which the logic signals are entered into the logic analyzer. So here the output of the probe buffer is applied to a latch at regular intervals. So the memory block is used to store latch data, which is finally displayed by the microprocessor. This is the microprocessor. So now you have to display data on the display. So actually whatever the data collected from latch, you can display on the display system. So your external clock and internal clock signals are used to clock the latch. So an external clock pulse applied to probe buffer used for synchronous operation. So this operation is called the state analysis. Your logic inputs are stored into memory. So this is the memory block during rising or falling edge of the clock. This logical information is list at the end of each clock state. So logic data in synchronization with the system under test can be captured in synchronous operation. So this is the state operation of the state analysis. So next one, in timing analysis. So in timing analysis, internal clock is used. Internal clock is used. Hence, the logic signals can be monitored on a continuous basis. In this analysis, the internal clock pulse continuously clocks the latch. So actually now we are providing two clocks to probe buffer. One is the external, other one is the internal. So your internal clock runs asynchronous to the logic system under test. So the clock pulses which are not useful for logic analyzer are ignored by the clock quantifier. The data stored in the control unit of logic analyzer must meet certain requirement. Hence, the memory block can be protected from overuse. So here actually this is the operation of the timing analysis. So that means here the internal clock runs asynchronous to the logic system under test. This is called the timing analysis. Here the data stored in the control unit logic analyzer must meet certain requirement. Hence the memory block can be protected from overuse. So this is the operation of logic analyzer. Once again, uh, uh, I will tell operation of the logic analyzer in two types. So one is in state analysis form, and another one is in timing analysis form. First one is the synchronous operation, second one is the asynchronous operation. So this is the idea about operation of logic analyzer. So next one, so I will give explanation for the signal generator. So already everyone knows idea about the signal generator. With help of signal generator, we can generate sine wave, square wave, triangular wave. So actually your signal generator is a vital component in a test setup and in electronic troubleshooting. So actually your signal generator has a variety of applications. So check the state gain, frequency response, alignment in the receiver. It provides a variety of waveforms for testing the electronic circuits. So actually here to test electronic circuit, we need the help of the input signal that may be in the form of sine wave, square wave, or triangular wave, so like that. Whatever the input, that input we will consider as testing signal for the any circuits. So actually here with the help of signal generator, you can generate such type of waveforms. So actually in a signal generator, the oscillator provides an sinusoidal output signal. Here the generator provides the sine wave, square wave, triangular wave. So amplitude modulated waveform. So requirements, the frequency of the signal should be known. The amplitude should be controllable small values of relatively large values. The signal should be distortion free. So that means here with the help of signal generator, so you can generate different types of waveforms, sine wave, square wave, and triangular wave like that. But is also having, that means you can generate such type of signal in different frequencies. In the same way, you can maintain different timings also. So every time we can change frequency and timing of the sine wave, square wave, triangular wave like that. So now this signal you should generate without distortion. That means the signal should be distortion free. So actually in our laboratory you can find signal generators in the form of function generator. So that having some amplitude adjustment and frequency adjustment, frequency selectors, so like that. So with the help of frequency selector, you can change frequency of the sine, frequency of the signals. So actually your signals in different frequency bands. So you can observe like this. So band approximate range for audio frequency is 20 Hz to 20 kHz. Radio frequency is greater than 30 kHz. Very low frequency 15 to 100 kHz, low frequency 100 to 500 kHz, broadcast 0.5 to 1.5 MHz, high frequency 1.5 to 30 MHz, very high frequency 30 to 300 MHz, ultra high frequencies 300 to 3000 MHz, micro ranges is greater than 300 MHz from 3 GHz. So these are the signals in different frequency bands. That means with the help of frequency selector, so you can generate waveforms in this range. So this is the use of the signal generator. So actually to generate signals, we need the help of the oscillator and the attenuator. That means here signal generator is a combination of the oscillator and generator, attenuator. So actually your oscillator is the sine wave generator. For example, Wien-Bridge, RC phase shift. So many types of oscillators are there. With the help of that oscillator, we can generate our required sine waves. So now with the help of attenuator, we can improve the output of the oscillator according to our requirement. That means you can attenuate the output of the oscillator with the help of attenuator. So actually whatever we need, so that output we can collect from the attenuator. So here generally you can observe two types of oscillators, AF oscillators, fixed and variable frequency audio frequency oscillator. So here fixed frequency of AF oscillator, a self-contained oscillator circuit is an integral part of generate a signal at specified audio frequency range 20 Hz to 20 kHz. The fixed frequencies might be 400 Hz audio testing signal, 1000 Hz existing a bridge circuit. So that means here fixed frequency AF oscillator is a combination of the audio testing and existing a bridge circuit signals. Actually your audio testing signal 400 Hz and existing a bridge circuit signal 1000 Hz. So oscillators can be easily generated by the use of iron core inductor. So now here iron core inductive coupling between the primary and secondary winding is to obtain positive feedback. That means here with the help of iron core transformer we can create oscillations. So here that oscillations we will collect in the form of sine. So this is the idea about fixed frequency AF oscillator. So next one, variable frequency AF oscillator generates a audio frequency signal in the range of 20 Hz to 20 kHz, fairly constant pure sinusoidal wave output. So now with the help of basic standard signal generator you can understand fixed and variable frequency AF oscillators. So actually your basic standard signal generator is sine wave. The sine wave generator consists of two blocks. One is the oscillator and other one is the attenuator. So accuracy of frequency, stability, freedom from distortion depends on the design of the oscillator, while amplitude depends on the design of attenuator, basic sine wave generator. So actually this is the basic block diagram for the basic sine wave generator. This having some set frequency, you can call as oscillator. So with the help of this oscillator we can generate sine wave. So now with the help of attenuator we can set the level of the frequency of the oscillator. Finally we will get output in the form of radio frequency signal. So this is the function of the basic sine wave generator. So actually this is the modern laboratory type of signal generator. So next, in the next class I will explain function of the signal generator. So simply you can call as the function generator. So okay, thank you.